All right, good afternoon, everyone. For no reason in particular, I'm helping with the introductions this afternoon. Our first speaker is Robert Layton. Robert's been giving the same presentation for about 4 years now. I think the content keeps changing, but he's a regular. The feedback, I get to see some of the post-conference feedback. Robert's feedback's always very strong, learned a lot. So I don't think he can get a much stronger indication that he's going to be a competent speaker. So everyone, have a good session.
Thank you. Thanks. How's that? Everyone can hear me? Yes? Soft? Okay, I'll just talk louder. All right. Yeah, so my name's Robert Layton. I wear a number of hats. I run my own consultancy firm called Data Pipeline. I'm also a research fellow at Federation University, where I look at applying data analytics to cybercrimes, particularly around attribution. I've also been doing some training for Python charmers, and I'm also a hacker at the Ballarat Hackerspace, so that's where I'm learning hardware and integrated chip development and stuff like that. And I got an email this morning saying that my new book is out. So Learning Data Mining with Python is out. So feel free to grab 3 or 4 copies. Thanks. Today the task is to predict the winner of an NBA game. So NBA is the American Basketball League. It has a couple of unique, perhaps not unique properties, but some special properties that are worth mentioning. The first is a lot of NBA games are played throughout the season. For those that probably don't follow it, there are 30 teams, 29 from America and 1 from Canada. They play several times a week for about 3 months or something like that. Most teams play about 80 games. I think it's 80 games off the top of my head. And we have 1,230 games per season before the playoffs. And then there's a whole bunch of playoff games that are played as well. So as far as sports go, it's actually a pretty rich data set. One difficult thing about NBA games is in most games, the score is something around the lines of 100 to 90, with some variation both ways. A huge percentage of games are decided by less than 10 points. And when you take those percentages and compare it to other sports, NBA is a very close game. So our task today is not particularly an easy one. But what we're going to do today is we're going to extract some features from a standard data set. We're going to create some new features using pandas. We're going to chuck that into scikit-learn. We're going to use our previous newly learned information about random forests and then build a classifier and see how well it does. So that's what we're aiming to do today. And this material is also loosely based on chapter 3 of my book. Hint, hint. So the data we're getting can be found from basketballreference.com. It is very comprehensive. It contains the results from games going back 40 years. It has player stats, location stats, league standings, who the most valuable player was. It is very comprehensive. The one thing it doesn't have, and I'm just preempting a question for the end here, is it doesn't have the odds of the teams going into the match. So I can't answer the question of how much money this would have made. So if you want to replicate the data, I'm not going to distribute the files because I'm not sure I'm allowed to, but you basically go to one of these pages and you click this export button here and you get exactly the file that I used to load up. We are using Python 3.4, Pandas, which is pretty much recent. 3.5 is still heavily development. Pandas 0.16, which I think is fairly recent, and scikit-learn 0.16. There's not a whole lot in this talk that requires such recent versions. Both Pandas and scikit-learn can probably go down a few versions, so don't worry too much. So the first thing we do is we load this file, which is NBA 2014 games.csv. And what What that is going to give us is it's going to give us what's called the box scores for each of the NBA games in that season, which is basically who the home team was, who the visitor team was, and how many points each of them scored. And it's always important to start with the end in mind, and for that reason, we're going to create our scoring mechanism. We're going to use the F1 score predominantly in this talk. The F1 score is for those with some data mining experience, block your ears. For those with no data mining experience, it's loosely correlated to the accuracy, but it's less likely to be biased by certain factors. All we're doing here is we're creating a scoring function, which is the F1 score. We care about both wins and losses for the home team, which we'll get to in a second. If we don't have this, it will only care about wins, and we want average weighted, so we care about the results overall. It's not 100% important, just let it be known it's roughly accuracy. So this is what our data looks like. Date, teams, their scores, a couple of unnamed columns, one which is completely pointless, it just says box score, and 2 columns at the end. I don't think this is used at all, and all this column here indicates whether there was an overtime. Another property about NBA matches is there are never draws. If there's a draw at the end of regulation time, they'll just keep playing overtime until there's a winner. So it makes it a bit easy, whereas with an AFL match, for instance, we would have to factor in draws into our calculations. Teams either win or lose, so that's pretty easy. So once we've loaded our data set into pandas using the read CSV function, it's had a look at our date column and didn't quite know the format, so it just read it all as strings. We're not going to use the date at all today, but I would like to fix that. And we'll also fix up the headings. So to do that, we can set the date column to be parsed as a date, and that means it will just try a bit harder. And you can see there that I think I don't show the D types, but the date's in a different format to what it is in the file. It was represented as a date-time object. So we could now, for instance, compare 2 dates if we wanted to. And also our heading names are a bit better now, so we can work out what this column is. So what we're going to do now is we're going to create the thing that we're going to try and predict. We're going to take this data set and we're going to create a classifier that will determine whether the home team is going to win that game or not. So we're going to create a new feature, which is called home win, and it's going to be the result of whether visitors' points was less than home points. It will be true if the home team won, and it'll be false if they did not. So you can see there with the first game, Indiana Pacers were the home team. They scored more points in Orlando, so they won. Pretty straightforward. And the next thing we do here is we grab those values, so y true equals. We grab the values here, and that's going to be a NumPy array. And those are the values that we're going to try and predict. There's the D types. And also, when you start a data mining task, it's important to know what the baseline is. Very simple baseline here is chance. If we were to just predict randomly, how accurate would we get? The answer to that is 50%, which is not quite the F measure, but we'll just ignore that for now. A better baseline for sports is the home team winning. For most sports, the home team will win more games than the visitor team. This has been widely recognised and is also true of NBA. So the home team will win 58% of matches. So if we want our model to be useful at all, we need to beat that measure. So if we convert that to an F measure, all we're doing here is predicting home team wins. So you can think of this as a very simple classifier. We just predict home team wins all the time. and then we use our, not quite the score we coded before, but the same parameters. We calculate our F1 score and we get 0.42, or 0.43 if we're going to round that way. So that's the score we need to beat. So we're going to create some more features because we're going to make a classifier that's a little bit better than that. So the first features I thought about were what did the teams win their previous game. So we're going to create this in a very inefficient way here, and I'll show you how to create it more efficiently, or create a similar feature more efficiently in a minute. So what we do here is we create a default dict, which will default to 0 the first time a team is asked for, and that's going to be whether the team won their last game. We then iterate over all the rows. We get the home team and the visitor team, and then we look them up in our onelast dictionary to see whether they won their last game. So if they won their last game, home onelast will be 1 or true. And if they didn't win their last game, it'll be false. So we grab those values, set that to home last win and visitor last win, and then set that row. And then we update our one last with whoever won the current game. So what we're doing here, iterating through the games, creating these new features, which screen was a little bit off here, but creating these new features, which is whether the home team won their last game, and then updating our dictionary so that the next game we come across, we know whether they won their last game or not. How many people were here for the random forest talk before? Great. So for those that weren't here, sorry. But we're going to start off by using a basic decision tree classifier. And all that does is just look for a value and split at that point. So if they won their last game, we'll go down this path. If they didn't win their last game, we'll go down this path and decide from there. So using just these two features, not even taking into consideration the home team explicitly, we've already improved upon our baseline with an F1 score of 0.5. So we're starting to get somewhere. So the next thing we're going to do is extend that feature a little bit, not just whether they won their last game, but whether they're on a winning streak. Winning streaks in the NBA are a little bit troublesome to consider. If a team has won 3 or 4 games on the trot, that might actually fatigue them and be a negative thing. But let's have a look anyway. So same procedure. The only difference, so we look up their win streak here. The only difference is rather than just set whether they won their last game or not, we increment the counter for the winner and we set it to 0 for the loser. So this is their win streak. No other change from before. And this is slightly better, but we use a couple more features. So we include the last win for both teams and the win streak, and then we create a new decision tree classifier, and we're slightly better. So at this point, I'll explain 2 more things about what I've done here. The first is a small point. I've set the random state to be 14. This means that you should be able to take this code with this data and get exactly that score. Decision trees have some element of randomness in them, not much, but this is more important when we get to random forests. By setting the random state to a specific value, all that randomness will happen in a deterministic way, and you'll get the results I do. Cross fingers. The other thing we're going to do, which is somewhere where I've forgotten to set the random state, is cross-val score. So this is where we do cross-validation. A couple of talks have previously mentioned it. Basically what we do here is split our data into chunks, which we call folds. We keep one of them out as our test data. We train on the others and test it on that test data. And then we change which fold we use for our test data. And we do that until all folds have been used as test data once. So then that's why we have this line here, which does the mean of the scores, because Our scores coming from cross-val score will be the the evaluation on each of those folds as a test set. So we get the mean that way. Just using features that we derive from basic game information, nothing about players, nothing about any sort of context about the things, we're able to already improve upon our baseline. But I thought, what about general stand-ins? So the NBA calls it a stand-ins, AFL calls it a ladder, so I'll use the word ladder. But basically what this is where the teams ranked in the previous season, whether they had the best win-loss ratio or not. So what we've done here is we've had a look at the stand-ins for the previous year, loaded that using pandas as before. I've had to skip the first two rows because they were mostly blank. Well, the first row was blank and the second row had some needless information. And the other thing I've done here is set the index column. Without that, pandas will create a new index down here, starting at 0. And then in order to do a lookup for a team to see what their ranking was, we would have to basically iterate through everything to find that team and then see what their ranking was. We set the index column to be the team, and that allows us to look up the pandas data frame directly by the team name and get their rank. So that makes the following code a little bit easier. So this is the stand-ins from the previous season. This is all information that you would have coming into a game to try and predict who's going to win. So we're going to do a feature which is very similar to our home team won last feature, but instead of looping through all the rows directly, we're going to use the apply method in pandas. So what apply does, and we'll start with this line here, we take our data frame and we're going to apply this function across each row. So axis equals 1 will go through each row for us, apply the function to the row, and then get the result. The result from here is a series, which we can then use to create a new feature, which is this one here. So our function looks like this. We take our row as a parameter, we get who the home team and the visitor team are, we ignore the next 4 lines for now. We get the ranks for each team, these two here, and then we see which one was better. Lower numbers mean a better rank. So the result here is if one team ranks better than the other, this will be, if the home team ranks better than the other, this will be true and false otherwise. The 4 lines in the middle is just a little annoyance of the NBA seasons across those 2 years, at least from a data perspective. There was a team name that changed. The Pelicans turned into the Hornets, or the other way around, I forget. So we just have to fix that. So where we see, oh, that's right, yeah, Hornets turned into Pelicans, so don't know why. So where we see the Hornets, where we see the Pelicans as a team name from the 2014 season, we have to convert that to the Hornets to look it up in the 2013 season. So with this bit here, we've added the results here as a new feature, and if we print out our results, we can see home team ranks higher as a new feature for us to try out. So using the decision tree classifier again, we really increased now. I think the last one was much lower than this. So same this classifier as before, cross-validation score on our new data, and 0.59. So just these basic features already getting us quite a good model. The other thing to note about the previous model is we used all defaults for the decision tree classifier. At no point did we try and change any parameters to try and improve the model there. For decision trees, this doesn't matter too much. There's not a huge amount of impact. the different parameters don't make as huge an impact as, say, a support vector machine or something like that does. But we can have a look. So something that was alluded to in some previous talks was this grid search CV. What this will do is it will take some sort of parameter space where we list the parameters and all possible values, and it will try all different combinations. So in this example, we've just got the one parameter with values from 1 to 20. The values above 4 won't be used in this particular case, but we then apply grid search CV here, take in our model, our decision tree classifier, our parameter space, and it will use cross-validation and try all the different parameters and see which model's the best. Because our parameter space is small, because our data set's relatively small, this can all happen in memory, so we don't need to worry about like the random walks that some of the other talkers spoke about, so we can just do it all in memory and we don't have too much of an issue. We get a very small increase here, 5925, 5945. So a little bit of evidence towards my claim that parameters in decision trees don't matter too much, but it's not 100% true. The next feature, and the last one of the normal features we'll have a look at, is whether the home team won the last game between these two teams. So the previous home team won last only looked at whether they won their last game, regardless of who it was against. This one just looks at the two teams specifically and whether they won their last encounter. So there's not a lot different here. I use a tuple and sort the team names so that we get a consistent key. So we're always looking up, regardless of who the home team and the visitor team is, it sorts them alphabetically, so we're always going to look up together. Usually the home team and the visitor team will swap between encounters anyway. So we then apply this to each row as before, get a new feature and call it home team won last. And this is our home team won last encounter. It'll be 0 if the home team won and the last encounter, and 1 otherwise. Grabbing all of this information out, we can see this gives us a bit more information. Using the same testing framework, we're up a little bit. But the change at this point hasn't been all that significant, so you wouldn't run to your boss and exclaim that you've solved their problem at this point. We've just got a little bit better. And it may just be due to noise, so we would have to test on other seasons. So that's basic information with just the box scores, just the history that we have from the single season and the stand-ins from the previous year. There's actually a lot more information in this data set, even though it looks very simple. It's also possible that some teams have a bit of a curse against other teams or something like that, where a normally lower ranked team might do very well against a specific team. Maybe the coaching styles match up better. So what we're going to do now is encode the actual teams as features. But this actually causes a bit of an issue because our home teams, as you can see here, are just strings. The bag of words model was brought up earlier. This doesn't apply here. These team names are specifically categorical values, but our classifier still won't take them. So a naive way here would be to just give them all numerical values, such as the Indiana Pacers being set as 1, Los Angeles Lakers 2, Miami Heat 3, and so on. The trouble with this encoding is that our classifier is going to consider, if we do exactly that, the classifier is going to think Indiana Pacers and Los Angeles Lakers only have a difference of 1, whereas the Indiana Pacers and Miami Heat have a difference of 2. So it's going to infer information that's not accurate there. But it is our first step. So we use what's called a label encoder. This is a transformer in scikit-learn. We fit it by giving it all the team names. It will assign a number to each team. We then get the home team numbers for each game and the visitor team numbers, and then we do a V-stack. So these are the numerical values assigned to each home team, and these are numerical values assigned to each visitor team. So this by itself has that issue I just explained, but it is at least a numerical value that we can start with. But that's one avenue to at least address that little concern. From here, we can use what's called a one-hot encoder. And what this will do is it will take each of our features, such as the number 7 for Chicago Bulls, for instance, create a new feature called was the home team Chicago Bulls, and it will be 1 if it was and 0 if it wasn't. So if we have a look at the result here for our home team features it created is 0's all the way, because it wasn't any of those teams, but it was this team. So whatever team this was, like Chicago Bulls, it set a 1 here that the home team was Chicago Bulls, and the visitor team was not any of these teams, but it was, say, the Los Angeles Lakers. This encoding has the property that you measure the distance between two things, and if they're the same, it'll be a 1. If they're different, it'll be a 0 or some value like that. And that's what we sort of want. We want to be able to compare these two things and get a same or a different value. So that's a one-hot encoding, and that's the most straightforward way to take some sort of categorical feature like team names and turn it into something that data mining algorithms can understand. Just using the team, so we haven't used our features from before, we get nearly at that 0.6 mark, which is, we got a bit over it before, we're a bit under it now. So we can see that there's information of a different type, but it's still getting to about the same mark. But then what if we try and use a better classifier, for instance? So decision tree here, random forest here, again, using default values at this point. Slightly better, wouldn't be too excited by this yet, but still around that 0.6 mark using just default values, but can we do better? So here what we've done is create a parameter space that has a few more features for the random forest, and we're applying our grid search again. So what this will do, we'll take this, and this parameter, try it, see the score, then go this, and this parameter combination and try to get the score, and do that for all different combinations and get the best result. And we can see there the result is much better. It says accuracy, but I haven't updated that bit. F1 score of 0.6436, and I think it's gratuitous graph time. No, not yet. So now what we're going to do is combine those team scores, the team features, which we got from the one-hot encoder, with our other features that we extracted before, and then do some classification on that. And we get around that 0.6 mark again. And then putting that into the full thing, we actually see a small drop in performance. This could be randomness related. It could be that some of the features weren't used properly, but it is about the same mark. So whenever you're doing data mining, don't get too excited by small differences, particularly if you haven't done a robust statistical framework to test whether it's significant or not. And we haven't done that here. Gratuitous graph time. So we can see here that when we use all the features, and this is for a slightly previous one where the 6.4 didn't happen with random forest because I didn't set the random state properly. So we can see here that tuned random forest will do better using all features. So these results are actually a little out of date. Ignore that. But generally that'll be the case. So, but tuned RF random forest did do better than the decision tree, and using more data is better than less as a general rule. One of the advantages of random forest is that while there is a huge amount of randomness to it, better features will tend to bubble to the top and get used more frequently. So adding data will rarely make your model worse, even if that data is noisy. But do be wary. So we have a model tested on the 2014 data that does fairly well. The real test here is, can we go one season forward and test it on the next season? So what I've done here is I've grabbed the recent games from the recently completed 2014-2015 season, and we'll load them as before. We get the stand-ins from the 2014 season, loaded as before, create our features as before, still going with the features. I've copied the code from before, changed a few things, but this is all just doing the same feature creation we did before. If you wanted to do this properly, and I haven't done it here, you'll create a pipeline like we saw in some previous talks. Set all this up to be separate steps in the pipeline, and then you wouldn't have to do the copy and pasting of code. So we have our data set here. Now this is important. The encoding of the teams have to be done with the same encoding that was used earlier. The reason for this, so what this code does, we take our label encoder from before, we take our one-hot encoder from before, and reuse those to transform the 2015 data. This doesn't matter so much on the other features, like home team won last, because they get recreated and put in the same spot anyway. But if you were to create new label encoders here, the teams might be assigned different numbers. And if they're assigned different numbers, then the one-hot encoding will create a different a feature for that team in a different spot that will be one that won't match up to the previous data. So we'll train on the 2014 data that we'll expect the Chicago Bulls to be feature 17. We'll test on the 2015 data where the Chicago Bulls are 15, and those rows won't match. And our classifier won't be able to use that information. So that's why we reuse the encoder and the one-hot transformer from before. So we've created our new 2015 data set, and importantly, we test the baseline. It's about the same as it was, which is actually pretty amazing that it was so consistent. 58% again, of 58% of games were won by the home team. So drum roll, we do a fit, and we do a predict, and we get an F1 score of 0.76, so significantly higher than our training data. That's a little bit confusing, but this is a great result. So things to keep in mind with this is it was higher than our training data, so we'd probably need to do a bit more testing, work out what was the cause of this, whether it was just a fluke that 2015 was easier to predict than 2014. Intuitively, I think that's true, but we might need to go back to previous seasons and try the same workflow out for there. So an F1 score is sort of like an accuracy, but it's not quite an accuracy. So I've also calculated the actual accuracy. So it is exactly the same in this scenario though. So just having a look at where our prediction is equal to the actual outcome, we get 76% of NBA games predicted correctly. So I think that's a pretty good result. So the next steps here are to incorporate betting odds, see if we can win money. These are surprisingly difficult to find. I have not been able to find a free resource that gives these odds, so if you know one or know someone that has them, let me know. The other thing to consider is to go much deeper into the data set. We can get information for how much each player played in each match, and their record leading up into that match. So we could incorporate that data, trying to keep in mind that we have to bet before a match, so we have to only use information that we had before a match. So we can't use how well a player did during the match, but we can use how well a player did in the previous match. But we do know which players are going to be in the team. So for instance, if LeBron James is playing, the Cavs have a much higher chance of winning, but if he's not playing, they're probably going to lose. So knowing whether he's playing or not is going to be a significant impact on whether the Cleveland Cavaliers win. And finally, AFL is the next thing. So Sportsbet and CIKM are holding a competition for AFL prediction. the winner will get $5,000. But more importantly, the winner will have won a competition like this. So, the link's there, but here we go. I'll show the URL. sportsbet.cikm15.com. So basically, they've given us information about the games from the AFL season and the players and stuff like that. Your goal is to predict the winners and predict the final season from this year. So this competition ends just before the final season starts, and then the winner is determined by who predicts the final season best. So, yeah. So that's my talk. Thank you for listening.
Thanks very much, Robert. Can we take a few questions? No questions. All right, I got a question.
Oh, hold on.
Oh, we've got one. Brilliant. No, you go.
Maybe the same question. Have you used this algorithm yourself to bet, and have you been successful?
No, I have a low tolerance to risk, so. but with the figures, I think
the odds are pretty good.
I think I'll try next year. Yeah.
Cool.
More? What was his question?
Not really a question, more of a comment. You can actually think about using TrueSkill. I'm not sure if you know what TrueSkill is as a feature. It could be quite interesting.
Yeah, that's a good idea. NBAs do record the offensive and the defensive ratings for players. So I forget the exact definition, but it's something like 100's the median. So a player on 100 is average, and a player better than 100 for offensive will score more points than not. A player lower than 100 for defensive will stop more points than not, so it's better in that way. But I think it's a similar thing. And that would be the most straightforward way to incorporate player data into this model. You get that offensive and defensive rating and put that in there. But yeah, TrueScore will work too.
It's just for your information, oddsportal.com has
Oddsportal.com.
all their history of pretty much every sport.
Great, thank you. Wait for my talk next year then.
I'm not really too familiar with random forests, but does the classifier output a probability of the win, or does it give a binary output? So you can get a probability. I've only here used the actual win or loss, but yeah, you can get a probability out of it. Yeah.
All right, I think this is probably going to have to be the last one.
I'm just wondering why, when you were comparing the ranking tables, did you just do a binary feature, like are they better on the standings, versus how far above me or below me are they?
Yeah, that could work as well. Yeah, a significant gap would be better than a lower gap, and that would be a good continuous feature to use. So yeah, that's a good idea.
Okay, everyone. So we'll be back here at 25 past. Just push it by 5 minutes, but one more final round for Rob.